So now to start our practice on our intro to synthesis problems. Before we do this is a good opportunity to remind us, because this is something, now that we've started to learn a fair number of reactions, and as we get into synthesis, we want to remember that many of these questions will often have the possibility of having more than one correct answer. Not all of them. Now, in most of these cases, as I've done with the key as well, I'm only going to show, what I consider to be, one of the most important or, the best answer, but it doesn't mean that that's the only correct answer in some of these cases. When it comes to synthesis, it involves sort of a new step, one that we haven't spent a lot of time with up until now. Most of the time we've spent with reactions has been looking at reactions, looking at our starting material, looking at our reagents, and trying to determine the product. But as we've discussed, when it comes to synthesis, in most cases, the way that we want to approach synthesis is by working backwards. And that's what I've tried to have you do on the first few problems here. We've got a number of problems where I'm giving you a product, and then we have to work to get to that product. Now, in this first case, these are relatively straightforward. We're going to work our way up in difficulty. But what I mean here is I'm giving you not only the product, but the reagent. And so all you need in question one is to figure out the starting material. So the way we do that is, look at the reagent. We're using bromine here. What does Br2 do as a reagent? And while there's certainly other things that it can do, at this point in the course, the primary thing that we've learned that bromine will do is it will add to an alkene to give us the dibromide. And given that our product here has the dibromide, we can fairly safely say that that's exactly what was happening in this reaction. And so that our starting material would be the corresponding alkene that could then be halogenated to give us the dibromide. Part B, we're ending with some sort of alkane, cyclohexane in this case. We can see that this is the product of a hydrogenation reaction. Hydrogenation, we know, works with alkenes. It can also work with alkynes to give us alkanes, but we know it's not going to be an alkyne here because we have just a six-membered ring, and we've learned previously that to have a ring with an alkyne in it, we need a significantly larger ring. So just some form of this cyclohexane with an alkene somewhere in it upon hydrogenation will give us cyclohexane. Part C is actually very similar to Part A. The main difference being that we don't just have bromine, but we also have water present. Very similar reaction to Part A, though. The addition of bromine and water to an alkene will give us the type of product we see here. So we know that in order to go backwards, we're going to remove the bromine as well as the alcohol and place in an alkene. All right, Part D, given that our reagents show us the presence of magnesium and an alkyl halide, we know that this has to be a Grignard. And that's really the only thing we've learned that we can do with magnesium. Now, our product has this section, the aromatic ring attached to a carbon. We know that's going to come from our electrophile in part 2. So then the Grignard reagent would have to be made from whatever the rest of the molecule is, which in this case is our alkene. So those are the 2 carbons of the Grignard reagent. And then we know that in order to make a Grignard, we need to have a halogen present. Our next part, we're using MCPBA. Again, like other reagents, there are multiple things you can do with MCPBA, but at this point, the only thing we've learned that we can do with MCPBA is to use it to make epoxides. Epoxides, remember, are these 3-membered rings containing oxygen. What's our starting material for making an epoxide? When we use MCPBA, it means we're making it from an alkene. Our next part, you can see we have this fairly complicated looking reagent here. We know that that's what we refer to as Lindlar's catalyst. And Lindlar's catalyst, recall, is a poison catalyst that we use for hydrogenation as opposed to just palladium on carbon. And the reason that we use it is because we don't want to fully reduce our alkyne. We want to convert the alkyne specifically into the cis-alkene that's pictured here. So knowing that, that means then that the starting material has to be the corresponding alkyne. Part G, we see ozone present. So we know that this has to be an ozonolysis. Ozonolysis, recall, completely cleaves an alkene and gives us carbonyls on both carbons of what was the alkene. So both carbons here, would be these 2 that are now both aldehydes. So the precursor or the starting material for this reaction would be, the carbonyls would be gone, and the 2 carbons that have the carbonyls would be attached with an alkene. All right, 2 more of these. We have sodium cyanide, and especially with the solvent HMPA, we know that's going to be an SN2 reaction. So for SN2, that means the nitrile substituted for some leaving group. That leaving group could be anything you want it to be. I'm choosing to use an iodine here, but it could be a bromine, it could be tosylate, whatever you like for a leaving group there. But the second piece, and also important, given that this is an SN2, we know that SN2 reactions proceed with inversion of configuration. So notice that when I went back to the starting material, I've inverted the stereocenter. And our final piece on question 1, we can see we've got a strong base. Our product is an alkene. And so we know that this is an elimination reaction. So we go back to essentially our alkane, and then we need some sort of leaving group present so that we can perform the elimination. All right, so now we move on to question 2. We're going to look at a different piece in question 2. In question 2, I've given you the starting material and the product. And what I want you to figure out is what reagents do you need to get there? And so in order to do that, essentially you need to figure out what's different. So part A, there's 2 things that have happened here. One is that our carbonyl got converted to an alcohol. The second thing is we've added a methyl group. So how do we do that in a single step? Well, that means, we know that carbonyls are good electrophiles, so we need a nucleophile that's going to add into that carbonyl, but at the same time, add a methyl group. And what better way to do that than with a Grignard? And if we want to be thorough here, we can then, put in our second step, which is to quench the reaction with water. Part B, you can see we have a leaving group, iodine, that's been replaced by a nitrile. So we know that's going to be a substitution reaction. In this case specifically, it has to be SN1. We have a tertiary leaving group. Regardless, though, the key piece of this question is we need a nucleophile to replace the iodine, and so we can do that with something like sodium cyanide. Part C, very similar question. In the starting material, we have a bromine. We've replaced it with an iodine. It's primary, the leaving group, so we know that this is SN2. So we need a good nucleophile that allows for incorporation of the iodine, and we can do that with sodium iodide. Part D, we've converted an alcohol into a carboxylic acid. We know that we can do that directly with Jones reagent. In fact, at this point, that's the only way we know how to do that reaction. Although if you were looking at these practice problems later on in the course, eventually you will learn some other ways to do that reaction. And part E, we have an elimination. We had the bromine in our starting material. We have the alkene in our product. And so we know that we need a strong base here to trigger elimination. All right, in part 3 now, we're going to put parts A and B together. What I've done now is I've given you a product and just said, find a single reaction that would allow you to make this product. And so this is certainly going to be a case where there's many possible answers. So here we have an alkene. At this point, we've learned, how many different ways to make alkenes. We could do an elimination. We could do a partial hydrogenation. We could say dehydration, although that's really just a form of elimination. So the question here is we just need to pick one of those and draw out the reaction. I'm going to choose here for no other reason than that's what I decided to draw. We'll do a dehydration. So we start with an alcohol. And we know if we treat that with acid and heat, we can cause a dehydration to take place, lose the alcohol, and end up with an alkene. Part B, we have an alcohol as the product. Again, there's a number of ways we've learned to do this. We could do carbonyl reduction. We could do some sort of nucleophilic substitution using water as our nucleophile. We could also do a hydration. So does it matter which one you choose? Well, it depends on the context. For what we're doing here, where it's just trying to figure out one reaction, No, any of these are valid answers. But if you were doing this as part of a longer synthesis, then yes, you would choose the one that helps you get back to the appropriate starting material as easily as possible. So again, it doesn't matter which one I use here. I can pick any of them. I'll go with the hydration. We know that we can do hydration of an alkene using water and acid to give us an alcohol. All right, part C, you can see we have a bromide. And that's one of the other things we want to focus on. For what we're going to be doing right now, we're focusing mostly on very, very simple functional groups or simple molecules. And by simple molecules, I mean molecules that typically only have a single functional group. And given that we know that alkenes don't generally do a lot, or alkanes don't do much in terms of reactions, that means whatever functional group we see is what we should focus on. So when it comes to making a halogen, in a lot of cases, we know we could use some sort of HBr addition. Here, though, this is actually would have to be the anti-Markovnikov product. And so, unless you're familiar with the anti-Markovnikov bromination, which we haven't learned yet, uh, we basically need to focus on substitution reactions, such as being able to use PBr3 to displace an alcohol with bromine. And finally, in part D, see we have a ketone. And the most straightforward way that we know to make a ketone is through oxidation of an alcohol. We have at this point learned one other method, which is the hydration of an alkyne. And that certainly could be a valid method here, but definitely a less common solution. All right, so our final part of this exercise is we now have 3 full synthesis problems. So we're going to take all of this together and start thinking about some actual synthesis problems. And while I have these as 2 separate questions, the retrosynthesis and then the forward synthesis, we're going to kind of work on them all together. So first of all, we're going to come up with a retrosynthesis for the problem, and then after that, we'll then pivot to the regular synthesis, the forward synthesis, I should say. So when we look at this one, we can see there's a lot going on. We've added a half dozen carbons. And so that should tell us we're probably going to be using some Grignards, because at this point, Grignard is really one of the only ways that we know to add carbons. What I also see then is an alcohol. And I know that if I had a carbonyl, I could make that carbonyl, or I'm sorry, I have an alcohol, and I know that I can make an alcohol while also adding carbons. So if I had this aldehyde, I could add a Grignard to that. That would add those last three carbons, the isopropyl group, and then would leave me with an alcohol. But as we can see, we're going to also need to add three more carbons. And the oxygen's not in the right place. If I wanted to add these three carbons using another Grignard, I would actually need the alcohol to be here. So is there a way that I can move that oxygen over? I can. It's not terribly efficient. It's going to take us several steps, but we can get there. So presumably, and I'm just going to abbreviate the aromatic ring with pH for phenyl, we could have made that aldehyde from an alcohol, and then we could have made that alcohol from an alkene. Finally, to get that alcohol on the previous carbon, we could have made the alkene that I've just shown by the dehydration of that alcohol. And finally, we could make that alcohol by the Grignard addition to the original starting material. So can we now do this in a forward direction? So first step, we want to convert the aromatic ring into a Grignard. We know we do that by adding magnesium. And then we need to add the proper number of carbons to make the compound pictured here. It's a 3-carbon piece that we're adding with the oxygen in the middle. So it turns out that's just acetone. And then, for completeness, we quench with water. Step 2, we need to dehydrate the alcohol to form the alkene. We can probably just use, weak acid here. This dehydration is going to be really, really easy because that alcohol, it's not only next to the aromatic ring, which means the carbocation is resonance stabilized, but it's also tertiary. So very, very mild conditions needed for that dehydration. Now we need to make the new alcohol. We need to put the alcohol on the other carbon. Notice that we took the alcohol which was on the most substituted carbon. We want to put it on the least substituted carbon. The way we've learned to do that is with hydroboration. So borane in our first step, followed by peroxide and base. We then need to convert our alcohol that we just formed into the aldehyde, which we can do with PCC. And finally, we'll add a second Grignard to put on the last couple of carbons. In this case, it's going to be the isopropyl Grignard, and that gives us our product. All right, question 2. You can see we're ending with a dibromide. And we're starting with a halogen, but the halogen we start with, that's bromine's not one of the bromines in the product because we can see they're not on the same carbon. So how do we make a dibromide? Well, the most straightforward way we know is to start with an alkene and add bromine to it. We can continue backwards, knowing again we need to make this alkene. We also need to add 3 carbons. again, at this point in the course, we're very limited on reactions that add carbons. So we know this is most likely going to be a Grignard, which means we're going to have an alcohol. And so that alcohol can be eliminated to give us the alkene. And then that alcohol, as we said, is formed by addition of the Grignard reagent to an appropriate carbonyl. And since that is kind of hard to read, we'll redraw that proper carbonyl down here at the bottom. All right, our final one, part C. So we can see we've got this nitrile as well as this alcohol. So how do we make this? Maybe a little harder here. We know how to make an alcohol with a bromine, but what about other functional groups? Well, sometimes one of the things we can do, and might be our best bet here, what if we had an epoxide? An epoxide, we know that if we open it up, will give us an alcohol, plus also adds whatever functional group we've added. And if, just so we can see that we've done this correctly, this methyl group is here, and then we have these two carbons are the two carbons of the epoxide. So in this case, the epoxide, we want our nucleophile to add at the less substituted carbon. So that means we use basic conditions. So KCN should work to open that epoxide the way we want it to. Now, to make an epoxide, there's only one way that we've learned to do that, and that's with MCPBA. And now, if you notice, we're actually in the same spot that we were in the previous question number 1. Notice this was actually the exact same spot we ended up at partway through. We had to make that from bromine, and so if that, or from bromobenzene, so if the way we did it worked above, why not use the same thing here? So magnesium followed by acetone, and then acid to eliminate that alcohol to give us the alkene. So you may notice as you're going through this exercise, there's a question 5. The question 5 is just to do the forward synthesis for each of these. And as I said, we were going to do the forward synthesis along with the retrosynthesis. So this is our introduction to synthesis, and as we learn more reactions, we're going to be able to do increasingly complex synthesis problems over the rest of this course.